brought to you by, let's see, who's this guy? This is Town Astronaut. So Lego Town Astronaut with his oxygen tank. Probably would not be wearing it until leaving the space shuttle, but whatever. Okay, so 2.5, we are going to figure out what's up with exponential growth. And in particular, what does it look like when we graph it? And then we're going to solve problems with exponential growth, and we're going to try to figure out what some of these parameters are for the equation, and then start finding and interpreting some models. And then in 2.7, we'll kind of tie everything together. We're skipping 2.6, by the way. So just a reminder, exponential growth is multiplication by a constant. That's how we tell that a sequence of numbers represents exponential growth. Now, if we're looking at a data set and we're looking at ordered pairs and whether those ordered pairs form an exponential model, we want to note that the multiplication by a constant is the same for a fixed number of steps. So if we look at an XY thing and our steps are going by 1 and we're multiplying by 2 each time, then we know this is exponential. But if these steps change and are not consistent, then we have to do a little more work to determine if it's really exponential. So the big difference right now between linear and exponential that we know of is linear is addition of a constant and exponential is multiplication of a constant. That's kind of the key difference that we've noted so far way back in section 2.1. So our author says, what do you think is meant by the relative change in a quantity? Well, first let's remind ourselves, what is the relative change formula? It's new minus old divided by old. This result is a decimal. And when we multiply it by 100, we get a percent. Remember, this means percent change in a value. So how much change has occurred from this old value to the new value? What percent increase or decrease has happened? Remember, relative change was the same thing as percent increase or decrease. So if you think about how we calculate a percent of something, for example, 10% of, let's say, $20, the way we do this calculation is we convert that decimal to a percent, we multiply it times the 20, and we get 2, or $2. So this multiplication is connected to this, right? If we multiply, if the change in our quantities increases by the same percent each time for each step, then we are definitely looking at an exponential situation. So here is some data. And our author says, hey, what's up? You got $10,000. What if you decide to save it and invest it, and you're going to let it grow for 40 years? What does this look like? So here's a table of values. Here's the first 7 years. So 7 is probably about right here-ish, right, in our graph. And here's the next 40 years. So if we're just reading our graph, in 40 years, it looks like you're going to have, what is that, almost $150,000. That's nice. So if you're in your 20s and you put away that $10,000 for those 40 years, there you go. When you're 60, you'll have $150,000. Not a whole lot of money, actually. You wouldn't be able to retire on that. All right, so for each value in the table after the initial investment, we're going to divide the amount by the value of the account the previous year. Remember, the way we found that multiplicative constant is we did the next value divided by the previous value, which is precisely what our author is asking us to do. So we'll take a look at some of these. 10,070 divided by 10,000. So that's the next value divided by the previous value. Here we get 1.07. We'll do another one. 13,107.96 divided by 12,250.43. Turns out, again, we get 1.07 or approximately 1.07. In fact, for all of them, all of the next divided by previously we get approximately really, really close to 1.07. Most of them are exactly 1.07. So for each one of these, 1.07, what does that tell us? Well, that says that if we multiply by 1.07 for each of these individual time steps, we get the next value. So, because we're multiplying by a constant, the data represents exponential growth. Okay, so now we're going to find the relative change, and we're supposed to find it for all values. So let's just pick these two. Remember how this works? We do the new value, so that would be year 7, minus the old value, that's year 6, divided by the old value. I'm going to go ahead and type this into decimals so you can see what's going on. So we got our 16,057.81 minus 15,007.30. I think it bears repeating that you need that parentheses. We want the calculator to do that subtraction first, then the division. And here's an example of a value that's really, really close. We'll do one more. So this is 0.07 if we round to 2 decimal places. Note that 0.69999933658, this is definitely 7.07. Most likely what happened is they had to round to the nearest cent, because that is the sensible thing to do with money. And so that rounding made it not exactly 7. Okay, so I'm picking just another random pair of values. Oops, I got too many decimals here. So 14,025.52 minus 13,107.96, and then we divide by that old value. And there we also get 7.07. So moral of the story here is that all of the values, all relative changes, are approximately 0.07. Well, how does that compare to what we found above? Doesn't there seem to be a connection here, right? This 0.07 and this 1.07. So this, if we recall what relative change is, we multiply it by 100. This is the percent growth. So our money grows at 7% per year. And it appears to be compounded. And then up here, this 1.07, this is the multiplier, and we call this thing the growth factor. So this is the growth factor. This we would call the growth rate, that percent change. Now notice we took this 7% and added it to 1, or the 0.07 added to 1. That's because when we invested our money, we put in $10,000, and that 100% of that money stayed in our account forever. We never lost any money. But then we continued to add 7% every year after our investment, which got us to 107%, which as a decimal is 1.07. That's what's tying this all together. Well, here comes the equation. So this is the model. The account started at 10,000. It grew by 7% each year. And we accomplished this by multiplying the year's amount by 1.07. So year after year after year, we continue to multiply by 1.07 repeatedly. So if we want the 10th year, we would have to have 10,000 times 1.07 10 times. Well, the shortcut for that is an exponent, hence exponential growth. So we would have written that to a 10. In general, if we want the xth year, the amount of interest in the account after the x year, we do 10,000 times 1.07 to the x value. So what we want to do is make sure that we get this in decimals. So I'm going to take that equation, and I'm going to type it in here. Y equals 10,000 times 1.07. I'll close the parentheses. They're not actually necessary. and then we're raising that to the x power. So I hit Shift 6 to make that happen. There's another way you can do it. This AB button does it as well. I'm going to teach you a little trick here. I can't see the graph, right? I could zoom around and I can try to find it. It's a little tricky. So one of the ways you can find it is click this gear button and turn your equation into a table. So then we see all these values, and click this zoom fit just like we did before. And now we've got a picture of the graph. Now it's not a great picture, so let's zoom out a little more. There we go. Now we've got a really good picture of that graph. And we can confirm with this table that we have the same numbers as what's in the table in the book.